this country's. I know this has nothing to do with calculus. But this is really shocking. And, sorry. So as far as I can tell, yeah, this is an ANFO explosion. It's the same stuff that was used in the Oklahoma City bombing, only much, much, much larger scale. Beirut's a modern city. And it's just unbelievable to see it looking like that. So if you're gonna play around with fertilizer, be careful, I guess. Really sad though. So if you have any intentions of traveling to Lebanon or have any family in the area, you might want to reach out and make sure they're okay. Today, we're gonna finish talking about parametric curves. So if you didn't see it, take a look at the video that I posted Monday evening about parametric curves. It was an intro to parametric curves and the basics of the calculus on parametric curves. I was only able to do one example of an arc length problem there because they take some time. So I'd like to do one more of those and also just take a quick look at some of the other sort of problems. So a quick recap of 10.1 and 10.2. A parametric curve is a curve in the plane defined by not one, but two equations. In terms of parameter, which is just another word for variable. And we usually use the symbol t because we're usually thinking about it as time. And the nice thing is that you can get all sorts of weird shapes out of these. So usually the way we think about it is I drop a little guy down on the page here. And you think of it as an ant. I set him down here at time t equals a. And then he walks along this path as t increases until eventually he finds his way over here at time t equals b. And at any point along the way, that point is in the plane, so it's x comma y. But instead of x and y being related to each other by some equation, x and y are both related to t. So I think of any point along this curve as x of t comma y of t. And you've got a function for x, which I just call x of t, and a function for y, called y of t. And then also, you're given some domain that t can run over. So here a is less than t is less than b. All right, so this is your parametric curve. At time t equals a, I set the ant down right here, and he meanders around according to these two equations. The first one tells you where he is in the x direction, left or right, at any given time. The second one tells you where he is in the y direction, up and down, at any given time. And these two things together we think of as the ordered pair x of t comma y of t. And that ordered pair represents a point. So as t changes, x and y both change, and you walk around the page. And then when we get over here to time t equals b, we pick the ant up off the page. Plain defined, yeah, this word defined. We saw how to do calculus with these curves. So if I wanted to find the slope of a tangent line, maybe right here, I can get the slope of this tangent line if I call this point x of c comma y of c. The slope of the tangent line at x of c comma y of c is equal to dy dx. That's what we're used to seeing, right? The change of y divided by the change in x slope. But this is actually going to be a function of time, t. So you take that formula and you plug in c for the time. The formula for dy dx has to be given in terms of these two equations because that's all we have. So you take dy dt, the derivative of the y equation, and you divide it by dx dt. And then you would plug t equals c into this to get the slope of the tangent line there. So you can do things like find horizontal and vertical tangent lines. We do that in the video that I posted on Monday. You can also find areas, the area under the parametric curve. You integrate from t equals a to t equals b, the function y of t times x primed of t dt. And this is actually the normal integral thing, right? You integrate y, usually y is what we call f of x times dx. Well, if x is a function of time, then dx is x prime dt. And f of x, we don't have an f of x here because this is not a function, right? This fails the vertical line test in a bunch of places. But you do have your height, which is y. So we can calculate areas and tangents just like you did in Calc 1. And if you haven't seen that video from Monday, please take a look at it. The operation I wanted to talk a little bit more about today is arc length. So we're only able to do one of those. So for this, because differential geometry is my baby, I use the symbol S, that's what everybody uses. The length of the curve, x of t, y of t, you integrate from t equals a to t equals b. The object we call ds, where ds is the square root of dx dt squared plus dy dt squared, all under the root times dt. In that video, I go through the derivation. You can write the formula in one line as the integral from a to b, square root of dx dt squared plus dy dt squared. It looks like a Pythagorean thing because it is a Pythagorean thing. We think of chopping that curve up into a bunch of little pieces, and then you approximate each of those pieces by a straight line, and the length of each of those straight lines comes from thinking of it as a hypotenuse of a right triangle. Nicholas, yeah, sure, here you go. So this is the idea. So if you're asked to find like vertical or horizontal tangents, you calculate dy dx as dy dt over dx dt. So here I'm giving you the slope of a tangent line at a particular point, but if you just want the general formula for dy dx, it's just dy dt over dx dt. Like I said, I'd like to run through at least one more arc length example. It won't be a tough one, but I'd like to do it. I think that would be good. So I'm going to come back to this page now. One more second. So I'm going to sketch a curve and then find its length. Or at least set up the integral for its length. So let's sketch a parametric curve, e.g. example. X equals, how about cos of t? And y equals sine squared of t, where 0 is less than or equal to t is less than or equal to 2 pi. And set up an integral for the arc length. So we could always make a table of values, and that will help us get a picture for what that curve looks like, or we can eliminate the parameter. Those were the two methods that we saw. The table will always work, but it can be a little bit painstaking, and it's not always easy to see how to connect the dots. So eliminating the parameter t to get the regular xy equation is, in some senses, the superior method. So here, y is sine squared. And sine squared is the same as 1 minus cos squared. We've seen that a million times. That's the Pythagorean identity. But cos squared is x squared. So this is the same as 1 minus x squared. So my curve is a portion of the parabola y equals 1 minus x squared. And I know what that looks like. One minus x squared, he looks like this. And then the question is, well, what portion of that do I get? Like, what's my starting point? What's my terminal point? What direction am I traveling? And how often do I travel this thing? So when t is equal to 0, where am I? Let's see, if I plug t equals 0 in here, I get x equals cos of 0, which is 1. And if I plug 0 in here, I get y equals 0. So I'm starting here at this point. This is my initial or starting point. Because that's the point associated with the first t value. Now, as t increases, say from 0 to pi over 2, cosine t decreases from 1 to 0. And sine squared will increase from 0 to 1. So as t goes from 0 to pi over 2, just getting started, my ant is walking along this way. And this is the point associated with t equals pi over 2. And so my ant will continue walking over this way. This is the point associated with, let's see, well, if I plug in t equals pi, cos of pi is -1, that's this. And sine of pi is 0, so this is the point associated with t equals pi. But then the ant does not continue walking down here, because this x value is never going to get more negative than -1, and the y value, sine squared, is never going to be negative at all. So really what happens there is my ant turns around and marches back this way. So we walk from here over to here as t goes from 0 to pi, and then we turn around and we walk back again over to here. So my initial point is also my terminal point. This is associated with t equals 0 and with t equals 2 pi. So as t goes from 0 to 2 pi, I start here, I walk along this path over to here, I bounce off of this and walk back along over here. I can illustrate this really nicely in Desmos. Desmos is actually great for parametric curves. You have to enter them as ordered pairs. And here what I would really like to do is add a slider for t if I can. I don't know why it's not, usually it gives me the option to. Yeah, here we go. So what you see is this, right? My little guy bouncing back and forth along that parabola. But he never goes outside the interval -1 to 1 because the cosine values never go outside -1 to 1. So the actual parametric curve is this blue portion. Yeah, it's neat, right? It was good stuff. You can do this with any parametric curve in Desmos, by the way, and I fully encourage you to do it as you work through the homework. It'll help you to visualize what's going on. So let's come back here. The question was, how do I know that cos squared is the same as x squared? Well, x is cosine t, right? So if I want to know what is cos squared, I just square both sides. So when I see cos squared t show up, I immediately recognize that as the square of x. That's all good. All good. So we've got our sketch. This is a nice sketch of the curve. We're able to figure out that it's a part of the parabola, and then we're able to figure out exactly what happens. So as t runs from 0 to 2 pi, I start here, I traverse this portion of the curve once, and then I bounce off and come back. If t just went from 0 to pi, I would start here and end here. If I want to find the length of this curve, then I should just do the arc length integral from 0 to pi, right? I shouldn't do 0 to 2 pi, because that would do this whole thing and then back. So the length of this curve is the integral from 0 to pi of ds, which is my square root of dx dt squared plus dy dt squared. So I'll do the length calculation on the next page. I need dx dt and dy dt. To find dx dt, I differentiate cos t, and I get negative sine t. dy dt, I differentiate the y function, which is sine squared t, and this requires the chain rule. That's 2 sine t times cos t. And then I can set up my integral. No guarantee that I can do the integral because these arc-length integrals tend to be horrible. So s, my length, is the integral from 0 to pi, the square root of dx dt all squared plus dy dt all squared. So that's integral 0 to pi. I'm going to write the square root as a 1/2 power to save my hands. Dx dt squared is negative sine t squared plus dy dt squared is 2 sine t cos t squared. And all this is being raised to the 1/2 power times dt. So that's sine squared plus 4 sine squared cos squared. And already I'm getting nervous because I'm not sure we can do this. Let's see, I could factor a sine squared, and then I'd have the square root of 1 plus 4 cos squared t. Yeah, I don't think so. I don't think we can do this. I think already we're to a place where this integral isn't manageable. I'll try to write it as nice as I can and see if we spot something. I factor sine squared, and then I pop it out of the square root as sine. And then what's left is the square root of 1 plus 4 cos squared t dt. This might be manageable. I guess my first try here would be to I'll use maybe the variable u, let u be cos t, du is negative sine t, my bounds change, 0 goes to 1, and t equals pi, goes to u equals negative 1. So this sine t dt, that's negative du. This is negative integral 1 to negative 1 square root of 1 plus 4u squared. We might be able to do this. Yeah, we can do this. This is a little bit scary, but it's doable. I can bring this negative in and flip the bounds. And then this is going to be a tangent substitution leading to a secant cubed integral. You see secant cubed show up a lot in these arc length problems. So the move here would then be let tan theta, 2 tan theta be u. So then du is 2 secant squared. Oh wait, no. Sorry. I need to let u over 2. Yeah. Be tan theta. So it's trig sub. It's a tangent sub. So then 1/2 du is secant squared theta d theta. And the bounds will change again. When u is negative 1, I will have the inverse tangent of negative 1/2. And when u is positive 1, theta will be the inverse tangent of positive 1/2, which unfortunately are not nice numbers. So then under this substitution, my integral goes from arctan negative 1/2 to arctan positive 1/2. 1 plus 4u squared will be u over 2 is tan theta. Did I do that right? 2 is tan theta. Maybe the other way is right, actually. Modulo of constant. 2. Yeah, because that's 2u all squared. Yeah, I'm sorry. So it should have been the way I wrote it the first time. 2du. This will be 1 plus tan squared theta. And then my differential is going to be 2 du equals secant squared theta d theta. So that's where the 1/2 will be. And this becomes a secant cubed integral. I'm not going to finish it. Oh, it's terrible. So you get 1/2 secant cubed theta d theta. I'll write it down. Why not? We're already here. So this is going to be 1/4 secant theta tangent theta plus natural log secant theta plus tangent theta, all evaluated from the inverse tangent of negative 1/2 to the tangent of inverse tangent of positive 1/2. All right, baby. Be careful. All right, so what you see right away is that these arc length integrals are friggin' terrible. They have a tendency to be savage. They have a tendency to land you in secant cubed territory, and often it requires quite a bit of juggling and substituting before you even get there. So fear arc length. Fear. I fear arc length, and I love this shit. But just acknowledge that arc length integrals tend to be a little bit rough. Well, I may ask you to do a computation on an exam. It's more likely that I ask you to set up an integral for the arc length. So here you could have stopped at this level, and I would have been okay with that. Even really, this would be okay. So that's parametric curves, really. Arc length problems tend to be a little bit scary. And you'll want to practice sketching parametric curves, like getting to a place where you can draw these nicely. That takes a little bit of practice. The eliminate the parameter trick can be done a few different ways. If you have sines and cosines, then you should try to use the Pythagorean identity. Otherwise, you should try solving one of the equations for t and then plugging that into the other. There are a bunch of different ways to parametrize. Yeah, so Thomas asked a really good question. How else can y equals 1 minus x squared be parametrized? So parametrized or parametrized is the verb for parametric. It means to rewrite that thing as a set of parametric equations. We absolutely could parametrize this as x equals t and y equals 1 minus t squared. Or another set of parametric equations that would work is x equals ln t and y equals 1 minus ln t squared. Or, you could use x equals t cubed and y equals 1 minus t to the 6. All of these would give that same parabola. Now, depending on the t values that you choose, right, we should also be specifying a t domain. If I want the negative 1 to 1 piece here, I would say negative 1 is less than or equal to t is less than or equal to 1. If I want that same piece here, I need to figure out what t values correspond to the x interval negative 1 to 1. And so here that would be e to the negative 1 is less than or equal to t is less than or equal to e. And here t would run from negative 1 to 1. The trick is you can pick pretty much whatever you want for your x function. And then your y function, you just plug in your x guy in the original equation. So I know I want y to be 1 minus x squared. So whatever I choose for y, it just has to be 1 minus this squared. So here it's 1 minus ln t all squared, because that makes this equation equivalent to y equals 1 minus x squared. Here, this is a t to the 6 because t cubed squared is t to the 6. So this is 1 minus this squared. And of course, there are other ways to do it, right? The trick for choosing your x function, I said you can pick almost anything. You want this to be a monotone function, meaning always increasing or always decreasing most of the time. And you want its range to be all real numbers. That will allow you to get any portion of the curve you want by picking the appropriate time domain. So like in the original problem we looked at with this one, the x of t equals cos t, y of t equals sine squared t. The reason I only got the negative 1 to 1 piece is because the range of my x function there was negative 1 to 1. If I wanted a larger portion of that parabola, I couldn't have gotten it with that parametrization. Sometimes you'll be asked to specify the x values that are a part of the parametric curve in question. And that is equivalent to finding the range of the x function over the stated time domain. So let's grab one from your homework. And then we're going to start talking about polar coordinates. So we'll do one here real quick. This is fun, isn't it? I like this. Some other fun shit, sorry, while we're here, classic parametric curves. The unit circle. All right, so you can parametrize the unit circle as cos t comma sine t. That's a classic that you should be familiar with. Yeah, so Thomas mentioned that we could reparametrize in different ways, and Morgan asked, why would we do that? Because the arc length integral, or I mean, whatever it is you're trying to do, find tangents, find arc length, find whatever, sometimes you can make those integrals or whatever calculation nicer by using a different parametrization. And if you look at the video that I posted from Monday, I do talk about that a little bit, how the parametrization we chose for one of the arc length problems, or one of the area problems, I guess, in that example, was much easier because of the chosen parametrization. Okay, so let's look at one of these parametric curve problems where we're asked to find, well, maybe they don't. They never do ask you to find those x values, do they? Eliminate the parameter, eliminate the parameter, calculate derivatives. Yeah, no. Okay, well, let's look at one anyway. So sketch x equals e to the t and y equals e to the negative 2t, where, what do I want to do with t? Let's have t run from 0, fuck it, to like natural log of 5. So when you go to sketch these, you want to figure out what graph it's on, sketch that graph, and then figure out what portion of that graph your parametric curve represents. Then you need, in other words, you need to find like the starting point and the ending point. And you also want to figure out what's called the orientation. Is your ant walking left to right or right to left? Sometimes, like in the first example we did today, it does both. So here what I see is that y is e to the negative 2t, which is the same as 1 over e to the 2t. And e to the 2t is the same as e to the t squared like this. So that's 1 over x squared, because x is e to the t. So my curve is some portion of y equals 1 over x squared. I know what y equals 1 over x squared looks like. Looks like this over here. I've got this vertical asymptote at 0. And then I have this y-axis symmetry. So this is the graph of y equals 1 over x squared. And then I just have to figure out what portion of that graph corresponds to my t values. You got to be careful. There is no t-axis here. And that's one of the mistakes people tend to make. This is the x-axis. This is the y-axis. There is no t anywhere in the picture. So the only way to figure out is by evaluating your function at the endpoints here, and maybe thinking about what happens as t grows from 0 to ln5. So our starting point, or initial point, I don't care what you call them, the book calls it the initial point and terminal point. This is x of 0, comma y of 0. So if I plug 0 into the x equation for t, I get e to the 0, which is 1. And here I get y equals e to the negative 2 times 0. That's also e to the 0. So we're starting at the point 1, comma 1. And then as t increases from 0 to ln5, e to the t increases. It increases to e to the ln5, which is 5. So here's 1, comma 1, and maybe here is, I'll put it here, 5. So here is my terminal point. My ending or terminal point is x of ln5, comma y of ln5. If I plug ln5 into the x equation, I get e to the ln5, which is 5. And here I'll get e to the negative 2 times ln5. It's easier if you think about it like this. It's 1 over e to the ln5 all squared. It's 1 over 25. And so I'm traveling like this. I set my ant down there. He walks along just this portion. Like that. And again, Desmos can verify. So if I take this x and this y and I write them as an ordered pair in Desmos, I expect to get just this part of this curve. I'll have a little ball walking from here to here. Let's see. What's this? Okay, let's see. Yep, there it is, right? Now here t is running over a different time domain. I guess I need to specify here that I want t to go from 0 to ln5, being steps of size, maybe 0.001. So there it is. And he's going to come all the way out here to 5, and then he's going to stop. Since I have this slider set to go back and forth, it'll reverse. So if we really wanted to be careful about this, for once, for indefinitely, but don't loop. I guess like this is probably what I'm asking for, right? Oh, and it reset to 10. That's annoying. 0 to 1. There we go. So see, starting at 1, 1, it's going to come all the way down here to 5, negative 1 over 25, and then it'll reset. So my parametric curve is just this part. Okay, so drawing these isn't too hard. We could do some derivative calculations, like I could find the equation of the tangent line here by using that dy dx formula equals dy dt over dx dt, and then plugging in the appropriate t value to find the slope. None of that is too hard. So take a look at the problems that I worked on Monday in that video, and then you should be comfy enough to do the homework. If you have any questions about that stuff, come see me in office hours, or maybe send me a picture of your work. Nicholas, I'm trying to follow the question. Could I ask you to be a little more specific? So we're looking at the equation and the shape it describes and seeing what portion of that shape. Yeah, so when you eliminate the parameter t, you get a normal xy equation with whatever that normal xy equation's domain is. And then you have to look and see over the specified domain for t, what part of that graph you get. So yeah, that's the idea. I think I understand what you're saying, and I think the answer is yes. So for these problems, you want to figure out, what does this curve look like? It's a portion of what graph? And then you have to figure out what portion of that graph. Those are the two kind of separate steps for graphing these. And you can always just make a table also, right? Making a table is a fine option. So I want to talk now about 10.3 and 10.4. 10.3 is an intro to polar coordinates, which you all saw in trigonometry, but I know not everybody remembers. And then 10.4 is calculus with polar coordinates. So these two sections together are about polar coordinates. The basic idea, you're used to thinking of the plane as being a bunch of points. Each point is made up of an x and a y. So you can think of the ordered pair x comma y as telling you how to get to a point by moving over x units and then up y units. There are other ways to tell you how to get to a given point. So if you hand me a point over here whose normal rectangular coordinates are x comma y, there is another very natural way to describe that point. And that's in terms of its distance from the origin, which we'll call r, and the angle you have to rotate, which we'll call theta. So the normal coordinates x comma y can be replaced by r comma theta. And the way this is usually taught is you go out r, and then you rotate up theta. Now the way to go back and forth is by using trig. I can drop a little right triangle in here, and then one sees that cos theta is the same as x over r, and that implies that x is equal to r cos theta, and sine theta, that's y over r. Again, just using this triangle, right? This length is y, this length is x. So you use your SOHCAHTOA. The sine of theta is this over this, y over r. And then you multiply both sides here by r, and you find that y is r sine theta. the last kind of important thing like this is that the tangent of theta is y over x. And also, I guess you could say, similarly important, if you take x squared plus y squared, that will be r squared. That's the Pythagorean. So this stuff here is like your map key or your dictionary for going back and forth from Cartesian to polar and polar to Cartesian. Cartesian is the word for normal XY stuff. So let's graph, example, graph the polar point r comma theta equals 2 comma pi over 2. Why not? So we have what's called the polar axis here. And I like to draw the vertical axis also, but some people don't. Here's how you do this. You go out 1, 2 along your polar axis, and then you rotate by pi over 2. And that gets me right here. So you don't need to draw this arc or anything. The point is just this point. So the Cartesian coordinates, this is the same as the Cartesian. It's named after René Descartes, the I think therefore I am guy, also the first guy to do any analytic geometry, first guy to think about the plane as x's comma y's. Same as the Cartesian point, 0 comma 2. Let's practice a little bit more. Three comma 5 pi over 6. Let's graph him. Okay, so I go out 1, 2, 3. And then I rotate all the way around 5 pi over 6. So that's going to put me right about here. So the length of this hypotenuse here is 3. And this angle through which I've rotated is 5 pi over 6. So that gets me to this point. Right? And again, you don't need to draw the arc or the radius like I am. You could just draw the point. It's going to take a little bit of time, Caesar, so try to be patient with me. Let's find the Cartesian coordinates. I can't quite tell what this guy is. I can tell that his x value over here is negative, that his y value is positive, but I'd like to find x and y here. So let's find the Cartesian coordinates. We know that x is equal to r cos theta. That's 3 times the cosine of 5 pi over 6. And the cosine of 5 pi over 6, we have to think about our unit circle. That's negative square root of 3 over 2. So the x here is negative 3 root 3 over 2, and y is r sine theta That's 3 times the sine of 5 pi over 6. That's 3 times 1/2. So y is 3/2. In other words, this point right here is -3√3 over 2, comma 1/2. That's the normal x-y coordinates. So Caesar, what we're doing to get to a given point, I take the r value and I walk out along my polar axis r units. So that puts me here. So this would be the polar point, r equals 3, theta equals 0. And then I imagine this as being on like a swing arm that I can rotate around, and I rotate around whatever theta value they give me. So here they told me theta is 5 pi over 6. So I walk out 3, and then I spin around 5 pi over 6, and that lands me right here. And the normal xy coordinates for that point, I can calculate using my dictionary. X is r cos theta, and y is r sine theta. So I just plug in for r and theta. R was 3, and theta is 5 pi over 6. And that will tell me the x coordinate. Same for y. I plug in for r and theta, and that tells me the y coordinate. We'll do one or two more. Let's go the other way. Let's find the polar coordinates for the Cartesian point xy equals, how about 5, 5? So okay, 5, 5 in regular Cartesian coordinates, I definitely know how to graph that. I go out here to 5, and I go up here to 5. There's the point 5, 5. I want to find the polar coordinates, so I need to find r and theta. Y equals r sine theta. So 5 pi over 6, sine of 5 pi over 6 is 3/2. Yeah. Oh, did I write 1/2? I'm sorry. Yes, 3/2. Thank you. Thank you. Yes, correct. Absolutely correct. Yeah, thank you for catching me. Okay, so let's come back to this guy. I want to find r and theta. So I want to find what is this distance and what is this angle. I know that x squared plus y squared is r squared. So r is the square root of 5 squared plus 5 squared. That's the square root of 50. We can simplify that a little bit, of course, right? That's 5 times the square root of 2. And then I know that tangent theta is y over x. Y and x are both 5. So theta here is the inverse tangent of 5 over 5, which is 1. The inverse tangent of 1 is pi over 4. So the polar coordinates are r comma theta equals 5 root 2 comma pi over 4. In other words, this distance is 5 root 2, and this angle is pi over 4. when I first learned this stuff, I didn't like thinking about it as go out along the polar axis, then rotate. I actually always thought of it as rotate first, then walk out a certain distance. Both are valid. You can do that in whatever order you want, but you do need to get to a place where you're comfortable graphing things in polar coordinates. There are some cheat codes for this. Polar graphing paper is your friend. So if I wanted to graph a certain point on this, like maybe 2, 3 pi over 2, I can think of these bold circles here as being like 1, 2, 3. So I'd walk out 1, 2, and then I'd rotate around 3 pi over 2, and that would get me right down here. So you might want to print out some polar graphing paper. It might be helpful for you. The question that I'd like to ask now is, and you may or may not remember this, how do we handle r being negative? And there's two good answers to this. So if theta is negative, we just rotate the opposite direction. If r is negative, you can think of it like instead of going out 1, 2 here and then rotating pi over 2, you go out -1, -2 here and then rotate pi over 2, which would land me down here. So I start by coming out to -2 and then rotating pi over 2. Believe it or not, that works. But there's another way to think about it. So let me label these points just so we don't get lost. This is the polar point, -2, 0. This is the polar point, -2, pi over 2. Another way to think of it is you graph the version with positive r, which would be this, 2, pi over 2, and then you reflect through the origin. Either one is a valid approach. The reflect through the origin thing is going to be important when we start graphing polar functions, because it'll help us understand certain kinds of symmetry in those graphs. But for the purposes of just finding the point and getting used to what it looks like, it's also okay to think about going out in the negative direction and then rotating. Both are valid, but the graph the positive version, then reflect through the origin is the way I'm going to teach this, because that's the way we'll need it when we're doing this today, talking about graphing polar functions. So let's do one more here. So if I want to graph the polar point, -3, pi over 4, I would first graph +3, pi over 4, and then reflect it through the origin. So I go out 1, 2, 3, and I rotate up pi over 4. That gets me here. Here's the polar point, 3, pi over 4. But then to get to -3, pi over 4, I flip this guy across the origin. And that gets me here. Caesar's asking a really good question. If we add pi over 2 to theta, that's almost correct. So we're adding pi effectively, right? This reflect through the origin business is the same as rotate 180 degrees or add pi. So polar coordinates are not unique. There's actually infinitely many sets of polar coordinates that will get you to this point. I could add 2 pi, and that would get me back to this point. Add 2 pi to theta, because that would just spin me all the way around the circle one more again. Or I could add a negative to the 3 and a pi to this guy. So polar coordinates are not unique. Let's do one last basic example like this. Let's find 4 sets of polar coordinates for the Cartesian point how about how about 0, 2? We'll keep it simple. I'm going to need some fresh paper. All right, so I want to find 4 sets of polar coordinates that get me to the Cartesian point 0, 2. So the Cartesian point 0, 2 is right here. X is 0, y is 2. So the most natural set of polar coordinates for any point have r positive and theta between 0 and 2 pi. If you force r to be positive and you force theta to be between 0 and 2 pi, then polar coordinates actually are unique. So I would say one set, r comma theta, that works here. The distance from the origin is clearly 2, and the natural angle, the most obvious one, is pi over 2. How else could I get there? Well, if I add 2 pi to this, then that just spins me around the circle one more time and lands me back at the same point. So another one would be 2 comma pi over 2 plus 2 pi, which is the same as 2 comma, let's see, 2 pi as a ratio over 2, that's 4 pi over 2, so that's 5 pi over 2. Yeah, very good. Morgan has some suggestions here with a negative r value. So let's try to find one with a negative r value. I know my distance from the origin is 2, so r has to be either 2 or negative 2. So let's pick r to be negative 2 and see what kind of thetas would work. If I come out to 2 and then I rotate, how could we say this? So let's use Morgan's suggestion. If I come out 2 and I rotate by pi over 2, that gets me here. I rotate negative pi over 2, that gets me here. So down here, I have this guy, and one way to describe him in polar coordinates would be 2 comma negative pi over 2, because I'm rotating in the backwards direction by pi over 2. And then if I reflect him through the origin, I'll land up here. So yeah, Morgan's suggestion, negative 2 comma negative pi over 2 does work. Could we find another one? Can we find one where r is negative 2, but theta is positive? Yeah, very good, 3 pi over 2, right? If I take the polar point 2 comma 3 pi over 2, I come out 2 and I rotate around 3 pi over 2, that would get me here. So this is also 2 comma 3 pi over 2. So if I make this r negative, it'll flip me back up here. So this polar point has these two representations. So their reflected versions will be up there. So -2 comma positive 3 pi over 2 also works. So here you see 4 different representations of this point in polar coordinates. All of those represent the Cartesian point 0, 2. So polar coordinates are not unique. That's one downside to polar coordinates, right? Cartesian coordinates are unique. I know that the point 0, 5 is right there, and there's no other set of coordinates in the Cartesian system that would get me there. There are ways to model this. Thank you, baby. So r comma theta will always get you to the same point as r comma theta plus 2k pi. That's the thing about being able to walk around the circle and get back to where you were. And it will also always be the same as negative r comma theta plus pi or theta minus pi. And you could even generalize this one a little bit to negative r comma theta plus 2k plus 1 times pi. So you walk an odd multiple of pi. So this is, if you wanted to, this is kind of a collection of formulas that will all get you to the same polar point. But I strongly encourage you to think about it in terms of the picture because of where we're going next. Where we're going next is graphing polar functions. And then we're going to start doing some calculus with those polar functions. Specifically, we're going to learn how to find areas. Areas are kind of the only interesting calculus operation in this setting. Derivatives are not so much fun. Nothing gets nicer when you think about differential calculus in this way, but integral calculus does get nicer. My wonderful wife brought me some coffee. Okay. So, graphing polar functions. Just like when we learn how to graph in the regular XY coordinate system, you're usually given like y equals some shit involving x, like y equals x squared or y equals 5x plus 1. Here, the variables that we need to relate to each other are r and theta. So it works the same way. Let's sketch the graph r equals 3. This is a constant function. It's analogous to like y equals a constant. So y equals a constant in the normal Cartesian system is a horizontal line. Here, r equals a constant. We can make a table of values, r comma theta. And you can plug in different thetas and see what r's you get out. So we can try theta equals 0, maybe pi over 2, maybe pi, maybe 3 pi over 2. So when when theta is 0, r is 3 because it's the constant function 3. When theta is pi over 2, r is 3. When theta is pi, r is 3. When theta is 3 pi over 2, r is 3. So I graph these polar, it is, yeah, good. Yeah, it's a circle. Spoiler alert, yeah. So if you ask yourself, what's the set of all the points whose polar coordinate has r equal to 3? Well, here's 3 comma 0. Here's 3 comma pi over 2. Here's 3 comma pi. Here's 3 comma 3 pi over 2. Yeah, it's just a circle. Why is this dope? Well, because circles in Cartesian coordinates have kind of complicated equations, right? The equation for this circle in Cartesian coordinates is x squared plus y squared equals 9, which is considerably more complicated than r equals 3, right? This is a constant function. This is anything but constant. In fact, it's not even a function, right? This fails the vertical line test. So while the Cartesian representation is not a function, the polar representation is. The Cartesian representation involves the square of x and the square of y. It's much more complicated algebraically than this, which is constant. So this is one example of polar coordinates making life easier. What you'll discover is that any time you're in a situation with a lot of radial symmetry, right, a lot of like circular symmetry, the polar system is going to simplify things. What is this point? Exactly halfway through quadrant 4. What's the r value there? And I could think of the theta value here as being 7 pi over 4. Or negative pi over 4. Right? All the points on this graph have r equal to 3, and theta is allowed to run wherever the fuck it wants. Okay. So circles centered at the origin. Radius k. Constant functions, r equals a constant, is a circle centered at the origin of radius k. What about theta equals a constant? How about the line theta equals pi over 3? Again, we could make a table. Theta here is a constant. It's always going to be pi over 3. So if r is 0, theta is pi over 3. If r is 1, theta is pi over 3. If r is negative 1, theta is pi over 3. If r is 2, theta is pi over 3. And we can graph some of these polar points and try to get a feel for what's going on. So this is just like in college algebra. When you're first learning how to graph functions, you can always make a table. 0 comma pi over 3, where is that? What are the Cartesian coordinates for that point? Or what's the name of that point? Yeah, it's the origin. If r is 0, you're at the origin. Always, no matter what theta is. 1 comma pi over 3? Okay, well, I go out 1 and I rotate up pi over 3. That's like here. 2 comma pi over 3? Let's do negative 1 comma pi over 3. So I would take 1 comma pi over 3 and reflect it through the origin. So here's negative 1 comma pi over 3. Two comma pi over 3, well, I would go out 2 and then rotate up by pi over 3. That will land me right here. So negative 2 comma pi over 3 would be the symmetric point over here. You can see what this is, right? This is a line through the origin. Whose angle with the positive x-axis is pi over 3. So theta equals a constant is a line through the origin. Theta isn't the slope, it's the angle that that line makes with the positive x-axis, but we'll just say it's a line through the origin. All right, that knocks out the two obvious things, the constant functions. My next favorite one, as we're getting used to this shit, r equals theta. This is less easy to see because the numbers that are usually nice for thetas aren't very nice for r's, and the numbers that are nice for r's aren't very nice for thetas. But we can make our table. God himself can't stop us. R is equal to theta. So if theta is 0, r is 0. If theta is pi over 2, r is pi over 2. If theta is pi over 4 or 5 pi over 4 or pi or whatever, then r is pi. 3 pi over 2, 3 pi over 2. So what's going on here? Well, as theta, we start out at the origin. And as theta increases, r increases at the same speed. The point pi over 2 comma pi over 2, let me throw another one in here. How about pi over 4 comma pi over 4? Well, I'm going to have rotated up by pi over 4 and also walked out pi over 4 units. Pi over 4 is a little smaller than 1. So if I mark this as 1, then pi over 4 is like right here. So the point pi over 4 comma pi over 4 is like right here. Then pi over 2 is twice as big as pi over 4. That's like here. So if I walk out pi over 2 and then rotate up pi over 2, it's going to put me right here. Pi comma pi, it's like right here. So let me label these. This is pi over 4 comma pi over 4. This is the polar point pi over 2 comma pi over 2. This is the polar point pi comma pi. It's a spiral. I think of this as a little arm swinging around and a little guy walking out along that arm as it swings. This is what's called an Archimedean spiral. In fact, if you watched the parametric equations video that I posted Monday, you've seen a parametric representation of this same spiral. I think Desmos can do polar shit. Let's see. New blank bracket. Polar coordinates. Somewhere under the options. Polar. Yeah. All right. So here I've swapped Desmos into polar mode. You can see like r equals 2, r equals 3, r equals 4, r equals 5. These are all circles. Theta equals pi over 4. It won't graph that for me, okay. But if I put in r equals theta, there you go. You get your Archimedean spiral. So here, as theta increases, r increases also, and at the same speed. So here's the point pi comma pi. Here's the point pi comma pi. Here's the point 3 pi over 2 comma 3 pi over 2. Here's the point 2 pi comma 2 pi. It's actually not the Nautilus shell. So Interesting. Yeah, Dalton, there is something very Fourier about this. To talk about that, we would need a little bit of complex exponentials. Unfortunately, we don't have time for it. But the Nautilus arm, the logarithmic spiral, is actually a little bit more, I think, maybe not that one, sorry, maybe it's, oh no, I was right the first time, it's e to the theta. We just gotta zoom way the fuck out. Yeah, so that famous golden ratio spiral, that's this guy. But they're similar. They're both spirals. All right, so that's some practice graphing, kind of fun toy examples. The sort of stuff that we deal with most of the time are trig functions. So now we're going to graph r equals 2 cos theta. All right, so not so much. It's true, it's true. I think Desmos kind of shit the bed there. It wasn't very happy. But let's try this. This is a little more like the sort of stuff we're going to be working with most of the time in polar setting. The way you want to graph most of these functions is first, so steps for graphing, I'll call them non-trivial polar functions. You don't want to just try to make a table. If you just jump in and try to make a table, you're going to end up with a bunch of points and it's going to be hard to see how they're connected. So what you want to do is graph r as a function of theta in rectangular coordinates, and then try to transfer that graph over piece by piece into polar coordinates. So first, graph r of theta in rectangular coordinates, or normal Cartesian coordinates. Then transfer the graph piece by piece into polar coordinates. So r equals 2 cos theta. That means I'm going to think of this as my r axis and this is my theta axis. Oh, we are just about out of time, aren't we? Okay. Shit. I suppose we'll pick it up here. Let me finish this example because we began it. If you can hang around, please hang around. If you have to leave, I understand. Just watch for the video. If I graph the normal cosine wave, r equals 2 cos theta, we always want to go at least out to 2 pi because I know I'm going to be moving into polar coordinates and I want to know what happens through a full rotation around the circle. That looks like this, right? We start here at 2, we come down as far as -2, and from 0 to 2 pi, r equals 2 cos theta looks like this. I want to make note of any important points on this graph, any mins, maxes, or x-intercepts. So this is pi. This guy here is pi over 2. This guy right here is 3 pi over 2, and that's 2 pi. And now I transfer into the polar setting. So again, I think about that arm spinning around. When theta is 0, the arm hasn't spun at all. R is 2. So I'm starting way out here. As theta increases from 0 to pi over 2, r decreases from 2 to 0. So I know that by the time my arm is up here, I'm back at the origin because r will be 0. But what's happening in between is a little bit tough to tell. R starts out here at 2, and as the arm rotates up just a little bit, R will have come in, but just a little bit. If I rotate a little bit more, maybe to pi over 4, R should be about here at root 2 over 2, which is something like this. As I rotate a little bit further, R comes in a little bit more and comes in a little bit more until I get to pi over 2 where R is 0. So I get a set of points looking something like this. Looking like this. Now, as I rotate past pi over 2, normally I would be drawing up here, but R is negative. So instead of drawing up here, I'm going to be reflected through the origin. If I rotate just a little bit past pi over 2, if R were positive, I would be right here. But it's negative, so I have to reflect it through the origin. If I allowed my arm to rotate just a little bit more, if R were positive, I would be out like right here. But R is negative, so I have to reflect through the origin, reflect through the origin, reflect through the origin, and you get this. So this is your polar plot, R equals 2 cos theta. It's a circle centered at 1, 0 and of radius 1. So this sort of stuff will take a meaningful amount of practice. And on Friday, I will show you how to graph lots of other things in polar coordinates. And I'll also show you how to find areas in polar coordinates. And then, ladies and gentlemen, you are done with Calc 2. Congratulations. This stuff, not too bad. It really depends on how much practice you got back in trig when you were supposed to have first learned about polar coordinates. So here what we've done today is essentially a review of all the polar coordinate stuff you did in trig. I encourage you to continue grinding and make sure that you are good at graphing these things. Practice going from this to this. If R is positive, it's fairly easy. The tricky bits are when R is negative. There's lots of good resources. Patrick JMT has a bunch of things. I will have my normal office hour this afternoon. That's what I'm about to switch to right now. And then I can try to put in an extra office hour on Thursday, but I cannot make a promise about that. So if you want a little bit more time to hang out and talk about problems, send me an email or a Canvas message letting me know, and I'll do my best to fit it into my schedule. That's as good as I can say right now. But yeah, that is it for today, guys. So I will, that's a shame. Yeah, some trig classes, they're not all created equal. It depends on who teaches, but they're definitely supposed to. Anyway, I got to go over to my office hour because I got other people waiting for me there. So I'm going to stop this. And if you want to talk some more, I'll see you in the office hour. Okay, normal link, the link that's on our main page in Canvas. We're back to the normal one.